for this optical nuclear transient, and you've already heard some this afternoon about how optical difference imaging is becoming a powerful technique for finding tidal disruption events. So I just wanted to review a little bit how we've been finding these exciting transients in the nuclei of galaxies. Originally, the first candidates were found in archival searches of the ROSAT All-Sky survey, which was a soft X-ray survey. And since then, people have been continuing to look at X-ray observations, mostly archivally, looking for flaring events in the nuclei of galaxies. But recently, there's been a lot more effort looking at longer wavelengths. I did a lot of work with the GALEX satellite at ultraviolet wavelengths, and now there's sort of been an explosion of candidates, or at least a real increase in candidates, by taking advantage of the cadence and area and difference imaging of optical time domain surveys. And so when I made this plot before, PTF and Assassin came out with their candidates, so there are even 5 more than are shown on this plot from optical surveys. And of course, we have these 2 candidates. So this is a plot of peak luminosity versus year of publication. So of course, we have these extreme luminosity tidal disruption event candidates, which we think are associated with jetted emission, and so are a different mechanism than most of the TDE candidates on this plot here. So why are we using optical surveys? Well, it's not necessarily the best place to study tidal disruption events, since you've probably heard from some of the theoretical talks that really we expect the bulk of the energy from tidal disruption events to be emitted at soft X-ray or extreme UV wavelengths. But in fact, what's really nice about optical surveys is their spectacular cadence. And with detailed light curves, we think we can actually probe the parameters of a tidal disruption event and really start to constrain the physics of what's going on in these events, and even use them as probes of black hole mass in distant galaxies. So unfortunately, we do not have a high cadence wide field soft X-ray survey. We also don't have such a thing in the UV anymore, and so we should build such space telescopes. But in the meantime, we're doing a lot of exciting work at longer wavelengths in the optical. So the candidate that I'm going to talk about today was a result of a joint effort between the GALEX Space UV telescope and the ground-based Pan-STARRS optical time domain survey. And we did an experiment called the GALEX time domain survey, where we did co-spatial and co-temporal observations with GALEX and Pan-STARRS. And these 2 telescopes were actually quite well matched in terms of their field of view and sensitivity. And so the idea was that if you're watching the sky with GALEX and Pan-STARRS, then you can catch things that are UV bright and not always depend on smart follow-up or being able to identify sources promptly in order to get follow-up. You get the near UV observations for free. So in terms of tidal disruption events, that's actually really powerful, because we know that tidal disruption events are intrinsically hot, and they really can be distinguished from supernovae, which are a lot more common in optical time domain surveys, because supernovae do not remain hot for very long. They cool off due to their expansion quite quickly. So here's this PS1 10jh, which we reported in 2012. This was detected as both a UV transient as well as a optical transient. And this transient was coincident with an inactive galaxy at a redshift of 0.17, and this host galaxy had very little signs of star formation going on, and it had a mass for which you would expect a few million solar mass black hole. So it seemed like certainly a galaxy that could host a tidal disruption event. And here is the light curve from pan-stars in the blue, cyan, green, and orange, and Galax in the magenta. And you can see that it has this very nice, smooth shape, a rise, and then a power law decay that's actually quite similar to the t to the minus 5/3 power law that you expect for fallback accretion in a tidal disruption event. And in our first paper, we fit the models that were available from Lodato et al. 2009, and we found a remarkable easy fit just by taking these models and scaling them the x-axis to fit the single band data. And just from this fit, you can get a constraint on the black hole mass of 2 million times the mass of the sun, but now you still have an uncertainty on the black hole mass because the mass and radius of the star disrupted is unknown. So the question is, before we get too excited, can we really trust this black hole mass? Well, there are a lot of details that have emerged as theorists have been thinking about this more carefully, and there are some basic issues where the most simplistic theory of this fallback accretion forming a disk around the tidal, with a size close to the tidal disruption radius around the black hole, doesn't really fit our observations. And so if you're going to trust this black hole mass first, you need to think about if we understand what type of star was disrupted. I'm going to talk about the spectroscopic properties in a second, but you're going to get a different black hole mass depending on whether or not you think this was a helium-rich core of a stripped red giant, for example, or if you think it was just a main sequence star. And then there's a lot of interesting questions of why is it that these UV and optical light curves are following the fallback rate linearly. You would expect band effects due to cooling of the radiation with time, and you would also expect much higher temperatures than we observed. We observed a temperature of 30,000 degrees Kelvin, or 30 to 50,000 degrees Kelvin. So there have been some ideas in literature of how to get around these problems. But we recently, or last summer, we obtained UV observations and optical observations of PS1 10jh with Hubble. And what's really neat is when you look now with Hubble, in the optical you basically just see the host galaxy light, but in the UV you see a point source, and that's shown with the magenta contours. And with careful astrometric registering of reference stars in the field, you can register the optical and UV images, and the cyan circle shows the 1 sigma uncertainty on the centroid of that magenta point source in the UV, and you can see that it's coincident with the nucleus of the host galaxy. So not only is this source still shining in the UV, but it is definitively within the center of the galaxy by 66 parsecs. So it is a nuclear source, and it's still shining in the UV. And so now if we look at its UV flux, it's remarkably continuing to follow these fallback rate models. So now I'm showing two models, one from Lodato et al. 2009, and one from a suite of models from Guillochon et al. 2013. And the Guillochon models fit some of the structure in the later portion of the light curve a little better than Lodato model. But you can see that basically the UV is continuing to decline close to these fallback rates and consistent with a t to the minus 5/3 power law. And this is 3 years later after the peak. So I mentioned the nature of the star, so there's a lot of interesting information in the spectroscopy of this event. And originally, when we published our spectra, we didn't have a very good late-time spectrum of the host galaxy. It still had some transient emission superimposed on it. So we used a synthetic galaxy template to isolate the emission from PS1 10jh. Well, now we have a better high signal-to-noise late-time host spectrum. So now we do a direct subtraction. We basically still get the same result. We still see these broad helium lines, these broad helium-2 lines, and as well as a hot blue continuum. And one thing I wanted to note is that with this late-time host spectrum, we do measure the equivalent width of H delta, and I didn't get to hear Yair's talk, but for this galaxy, we don't measure an equivalent width for H delta strong enough to be classified as an E plus A galaxy. So this may not be a rare post-starburst, but may be a more normal elliptical galaxy, early type galaxy. So I just wanted to focus a little bit more on these helium lines, because one of the most surprising things about the spectrum is not so much that we detect helium, but that we don't detect H-alpha. And so shown on the left is the broad helium line with a full width half max of 9,000 or so kilometers per second. And I'm showing the Gaussian fit to that line in green. And then the dashed lines show the full width half max of the line in velocity space. So one neat thing is you do see some excess in the blue wing of the line, and but even more interesting is the fact that when we look over at the velocity region near H alpha, we really don't see anything. Now I've hashed a region with red dots of where the telluric band correction is, so where you have to be a little bit cautious. But we really don't see a line. But I did integrate the flux between the dashed lines for both lines and took their ratio, and I get a ratio of 4.7 plus or minus 1.0. So I kind of use that as the upper limit or the lower limit on the helium-2 to H-alpha ratio. So we really don't see any broad H-alpha, and it's at least greater than 5. And this is very interesting because this is, you're going to hear more from Nathan Roth. We interpreted this extreme ratio as due to a lack of hydrogen in the star, but perhaps there are some photoionization conditions in a thick envelope surrounding a tidal disruption event that could cause such extreme ratios. But this, we really don't see any H-alpha to a limit of helium-2 to H-alpha greater than 5. Okay, so my conclusions our HST observations of PS1 10jh confirmed that the flare was nuclear. The late time flux follows the t to the minus 5/3 fallback rate, 1250 rest frame days after the peak. We confirmed the helium-2 to H-alpha greater than 5 ratio measured in our first paper with better host subtraction, and we do not classify the host galaxy as an E plus A, as claimed in Arkavi et al. 2014. So the implications, PS1 10jh really cannot be a supernova because it's maintaining a very bright UV luminosity over a long period of time, and you really cannot reproduce that with a supernova. And we really don't think it was a microlensing event. Its light curve doesn't look like one, and also the fact that it is nuclear disfavors a microlensing event, which would occur from a random star in a unseen foreground lensing galaxy. We still show the fact that the UV flux density still follows what we would assume would be the bolometric luminosity and the decline of the mass accretion rate, and therefore you can't have band effects that would change the behavior in the UV and optical bands compared to the bolometric luminosity. So we need some sort of fixed SED, and I think there are going to be a lot of talks giving ideas on how to keep your spectral evolution, how to keep your temperature fixed. We also need efficient circularization because we seem to rapidly be following the mass accretion rate without any delays in the radiative output. And then finally, the suppressed hydrogen emission could be the signature of the helium-rich chemical composition of the disrupted star, so perhaps this was analogous to supernovae. This would be a stripped tidal disruption event so that the star was already lacking its hydrogen envelope. But there's just recently, hot off the presses from Roth et al., some calculations which show some conditions in which you can get very extreme helium to H-alpha ratios with these optically thick reprocessing envelopes. So I look forward to learning more about that and figuring out what is the best explanation for our object. Thank you.
How do you technically do this?
That's a good question.
Thank you, Suvi. Can you hear me?
Yes, I can hear you.
We're going to take some questions.
Okay. Hi.
So, hi, Suvi. Question. Richard?
Hi, Suvi.
Hi.
What will it be reprocessing after 4 years now? If it's a big reprocessing screen, what exactly will there be in the middle which is producing this emission that it's getting reprocessed? Because you didn't see X-rays after 1 year.
So in the Roth model, which obviously I just read because it came out last week, the idea was that you could form this reprocessing envelope from the debris, and I guess you must be able, so in our case we would have to form it quickly because we see this helium, we see this hydrogen emission suppression at 22 days before peak. But then the idea, I think, in the model is that material from this envelope could be draining out over time. I don't think you would have a new source of material, but I think this envelope, and you'll have to ask the authors, but I think this envelope could persist for a while, but that might be also, I think what you're bringing up is that perhaps the long-term persistence of this emission could potentially constrain the model if it's hard to keep that envelope steady. Is that what you're implying?
No, no, I was really talking about the primary source of radiation that this envelope is reprocessing. Where is that coming from?
The primary source is continued fallback, so it's the light curve is following the rate at which you'd expect material to be continuing to return to pericenter from the initial disruption.
But then we'd see X-rays there, wouldn't we?
Well, we never saw X-rays, so when we looked with Chandra close to the peak, we did not detect any X-ray radiation, but that was consistent with a soft temperature. So basically a temperature a little bit less than 10 to the 5th Kelvin. So we didn't see any initial X-ray photons, and I don't see any spectral evolution in the UV, but it's possible you could look for X-ray emission now, but I don't know, I don't have a good reason to think we would see X-ray emission now.
Stephanie?
Just directly related to that. So I guess the key thing is that helium-2, in order to create the ion, it
Oh, okay, so we do get a lower limit to the temperature for how many photons you need to photoionize helium, and that is still safe, or it's still consistent with the upper limit on the temperature we get from the Chandra observation. So there's still enough extreme UV photons around to ionize the helium. And remember that Chandra isn't the ideal telescope because its soft X-ray sensitivity isn't that great. So, only being sensitive down to 0.3 keV or so isn't the best for probing the soft X-ray.
Sure.
Quick question, did I understand right? Are yours objects, the helium-2, had an asymmetry with broad to the red, whereas this one was broad to the blue, is that right?
No, so it's a little bit confusing because they're being shown at different scales, but I have this one plot where they're on top of each other, and it seems to be blue shifted, so it seems to be asymmetric with a longer tail to the red, but the peak is blue shifted. So what the blue axis that Suvi mentioned is where the peak would be, but hers had an additional component on top of that.
Nick?
Hi, Suvi. Is the late time optical non-detection consistent with optical also following t to the minus 5/3 and just falling below the host galaxy flux, or would it need
So
to
it's really hard to do a optical non-detection because with HST we have just this one epoch, and I don't see any morphological evidence for a point source in the center of the galaxy still shining in the optical, and based on the decline that you see in the UV, you wouldn't expect to detect any significant emission in HST. But in order to actually carefully do that, you'd need a second epoch, second late time epoch to do a difference image with the HST imaging. But based on how faint you expect the optical to be anyway, you do not expect to see it in the HST image clearly above the host.
One last question, someone? Please, Paul.
Any signs of release of merger in the HST image?
No, it looks it can be described quite well with the de Vaucouleurs profile. There's no evidence of disturbed morphology.
Okay, let's thank Suvi again. Thank you, Suvi.
Thank you.